respected faculty participants and industry participants, my faculty colleagues and students joining us today. It gives me immense pleasure to welcome you all to this IST-approved one-week online faculty development program on application of artificial intelligence in chemical engineering. In today's rapidly evolving technological era, AI is playing a transformative role in various engineering domains, and chemical engineering is no exception. This FDP aims to provide valuable insight into how these AI tools and techniques can be effectively applied in chemical engineering industry, research, and education. We are truly delighted to have such an enthusiastic participation from faculty members and chemical engineering professionals across various institutes and industries. Your presence has truly added great value to this program. Now, it is my proud privilege to invite Dr. Neeta Mehta ma'am, Head of the Chemical Engineering Department TSEC, to deliver a welcome address and share a few words with us. I request Neeta ma'am to kindly take over the session. Neeta ma'am?
Yeah, hi Tripti. I'm audible?
Yes, ma'am.
Thank you, Dr. Tripti. Respected Principal Dr. G.T. Thampi sir, our distinguished resource persons, invited guests, coordinators Dr. Ramesh Bhande and Dr. Tripti Dharamrao, the organizing faculty team members, and our impressive gathering of enthusiastic participants. A very warm welcome to each one of you. Good morning, everyone. Let me briefly introduce our institute, Thadomal Shahani Engineering College, formerly known as TSEC. Established in 1983 as Mumbai's first private engineering college under the HSNC board, TSEC stands tall today. We offer MBA and NEC accredited undergraduate programs in chemical engineering, computer engineering, information technology, artificial intelligence and data science, electronics and telecommunication engineering. We also foster advanced research through our PhD programs in these core and emerging sectors. At TSEC, we focus on the holistic development of our students, ensuring their placement in highly reputed companies. Our chemical engineering department was established in 1983 and is the oldest private department under Mumbai University. And it stands as a proud pillar of our institution's legacy. With a dynamic faculty, strong alumni network, state-of-the-art laboratories, and robust industry collaborations, we nurture and shape our students into industry-ready engineers. This marks our first IST-approved online faculty development program for the academic year 2025-26. An initiative like this wouldn't have been possible without the bold vision of our principal, Dr. G.T. Thampi sir. As a pioneer in AI, he has consistently pushed us to weave the artificial intelligence into the fabric of chemical engineering. His constant motivation and guidance were the sparks that ignited this FDP. Together, we are setting the stage to lead the way in AI-driven chemical processes and real-world applications. Friends, AI is no longer just a buzzword. It is a transformative force. Throughout this FDP, you will dive deep into predictive analytics, AI for sustainability, Gen AI tools, and rapid process simulations. You will explore innovative concepts like digital twins in the manufacturing sector and evolutionary optimization strategies. Thank you, Principal Sir, for your constant encouragement and motivation in bringing these advanced themes to the forefront. The overwhelming response and the diverse range of registrations we see today speak volumes about the collective curiosity regarding AI in our field. Participant, this is your opportunity to gain practical, high-level skills from our stellar resource persons, experts such as Professor Dr. Ravindra Gudi, Dr. Kishalya Mitra, and Mr. Pratap Nair, to name just a few. I encourage everyone here to participate actively and engage fully in every session. Remember, AI will not replace core chemical engineering. However, the industry will always prefer a chemical engineer with the AI knowledge over the one without. Let's make that knowledge our competitive edge. Enjoy the week ahead. Thank you. Over to you, Dr. Tripti.
Thank you very much, ma'am, for your inspiring word and setting the tone for this FDP. Your guidance and support are always a great source of motivation for all of us. Now, it is my honor and privilege to invite Dr. G.T. Thampi, Principal, Thadumal Shahani Engineering College, to address the gathering and share his valuable thoughts on the importance of emerging AI technology. But before that, let me take a few moments to introduce Sir to our participants. Dr. G.T. Thampi sir, Principal of Thadumal Shahani Engineering College, Mumbai, with a PhD degree in technology, comes with more than 34 years of experience in renowned colleges. Dr. G.T. Thampi has been part of some interesting researches and hold interest in business process and re-engineering in the realm of engineering education. Apart from his own researches, he has also been a guide for multiple researches done in the technology front and has contributed to the existing body of knowledge. 20 plus research scholars are awarded PhD under his guidance. Dr. Thampi is also an author of 85 plus research publications and book. Now, I respectfully invite Dr. G.T. Thampi sir to deliver a keynote speech. Sir?
Yeah. Good morning, one and all present here. Outside, I congratulate Department of Chemical Engineering headed by Dr. Dita Mehta. She massively succeeded in reorienting, re-energizing the department. Also, acknowledge the contribution of Tripti, Ramesh Bande, and other Mr. Joshi, enthusiastic in understanding evolving technology marketplace and technology and chemical marketplace. So outside, I like to introduce or demystify the backbone of AI. AI for majority identify with generative AI tools like ChatGPT, Gemini, Tiny Banana. Behind all these tools, there is an entity called large language model. Large language model is essentially an electronic brain created in massive data centers with cloud service. Data center with a lot of GPU and TPU, a lot of electronic devices, which consumes massive energy. The consumption of data center holding this large language model can be equated with energy consumption of a city. Therefore, the American state is finding it difficult to exponentially grow in AI application and research. They like to create more data centers. That is happening in India and Mumbai. Mumbai, there is a data center. It is IOTA by Dr. Niranjan Hiranandani. He is also our trust president. So electronic brain existing or hold getting hold by data centers, massive electronics setup. And that electronic brain, we say neural network. Electronic replica of human brain. Lot of technology, recent technology in the second half of 20th century. Now we are the quarter of 21st century. We could see a lot of technology breakthrough coming from imitating massively optimized human systems. One of that is neural network. There are some optimization algorithm called evolutionary algorithm, specifically genetic algorithm. Lot of algorithms, honeybee algorithm, ant colony algorithms, all either human replicating human systems or following the patterns of animal kingdom. Why scientists all over the world focused on understanding human behavior or behavior of animal kingdom, including small creatures, because this behavior is massively conditioned by years of existence. It's massively optimized behavior. Therefore, it's advisable to imitate. So scientists keep their eye and ear open. Today I read the molecular structure of cholesterol can be used for improving the speed of quantum computing. If quantum computer introduce a device based upon cholesterol molecular structure, performance multifold. So coming back to neural network, physically it is possible to imitate and create electronic brain. Now this LLM creators like OpenAI, who is owning this ChatGPT, they could heavily relying on tools created. There are multiple tools created by multiple actors in the realm of IT and electronics. And they realize, and also having natural language processing, no? They're having algorithm, not only OpenAI, a lot of other actors having complete control over natural language processing. Better than human being. Now, they created electronic brain, saved into electron data center, then mobilized all the digitized content from Wikipedia, from digitized content of libraries all over the world, from social media handles, accounts. They dumped that to train this electronic brain. So electronic brain is capable of holding trillions of data. So electronic brain is replacing lakhs of human being with higher cognitive ability. Electronic brain is outsmarting collective understanding in different fields. Collective understanding of the experts, experienced people is getting replaced by these artifacts. Collective understanding of medical science medical practitioner is getting replaced by LLM because that is fed with all the possible data related with medical science, medical practices. So that is the crux. By this time, majority of famed LLMs, whether it is from Google or Apple or Meta or Chinese, India is also making LLM, not yet released. By this time, this LLM gathered everything, anything and everything of chemical engineering. So it's the opportune time for chemical engineers and professors and teachers and students to understand this magical tool. Nothing great about reinventing the wheel. Leonardo da Vinci invented wheel 1600. So every time nobody needs to reinvent. Also understand that 1850s, there was a phenomena called gold rush. Gold rush happened in California. You remove some surface level earth, you're getting gold, that kind of scenario. People rush to that California from all over the world to mine. At the end of the rush, those who facilitated mining, those who supplied mining equipment, they made fortune than the miners. Chemical engineering practitioners and industry can take a cue out of this. Even otherwise, the AI proponents, Google or Microsoft or OpenAI is not making the money, the wealth created by NVIDIA. NVIDIA is not a AI company. NVIDIA is giving the chips required for the electronics required for setting up this data center and LLMs. They made more money. Their market capital, market value is $4 trillion. They exceeded $4 trillion within a span of 1 year. Outsmarted Microsoft, Apple, and obviously Google, OpenAI, etc. The most valued company in the world. Compare that with Indian economy. Indian combined value of Indian stock is trying to approximate 3 trillion combined, all stock taken together. One company, NVIDIA, not the original IT company, AI company. So take you out of this. Chemical engineers also can create massive wealth. You need not be the original inventor of AI, but you can leverage this AI because to get higher market share, the people who is releasing this in the marketplace is keeping the expertise required for using it low because they are interested in the higher market share. So therefore, they do all the no stone unturned mode to penetrate all the possible marketplaces. So there is not much expertise required to integrate all this in chemical processes and chemical industries, whether it is chemical consulting, manufacturing, or even education. People suffer from latency or inertia. That's the only barrier. as the title says, is transformative. If somebody evolved as a local champion, decide to seize the opportunity, can create catapult to a different orbit of performance in terms of the efficiency or the productivity. AI cannot replace chemical engineers or chemical engineering. Nobody can replace, AI cannot replace medicines, pharmacy, or specialty chemicals or fertilizer or pesticide. But you can make it more efficient and productive. Therefore, it's opportune time. Without much delay, you should be able to develop footprints of these aspects of AI. AI application, process engineering, development of new material, AI for environmental sustainability, energy solutions. So all the domains of chemical engineering can be energized, re-energized, reoriented by AI technology and practices. So you can, AI is essentially trying to create or simulate intelligent behavior to support decisions in process and design. There is a crux. The design process or the chemical process can be, or the design of equipments, design of process, all can be massively, drastically, radically modified to make it more efficient. There are jargons called supervised, unsupervised, deep learning, neural networks, reinforcement learning to model complex chemical behavior. So that neural network electronic brain can be trained with labeled data. Every data is labeled. This is density, volume, temperature, the color. Now a lot of so it can be fed with labeled data. They said labeled data. The outcome of some chemical reactions or chemical process or the outcomes of daily routine in chemical industry without labeling also can be fed to this electronic brain neural network. That is no supervised, they say supervised learning, unsupervised. A lot of algorithms evolved to make it more optimal. The supervised, unsupervised learning is essentially classifying the given data set, a clustering. Supervised learning for classification and unsupervised for clustering. Deep learning algorithms are essentially, these are superficial understanding, but this is essentially to help you to develop footprints of this. This should not be anathema for you, foreign body for you. Therefore, it's advisable that now you be familiar, friendly with these tokens. Don't get carried away hereafter. Deep learning is essentially more complex electronic brain with multiple layers. So that kind of multi-layer neural network can be used for forecasting, prediction, predictive analytics, engineering applications, historic, the evolution of it. It's advisable that how AI evolved over a period of time. In the early 90s, I was involved in a ME dissertation where I initiated one of my students to design of expert system for design of bridges. Long back, 1990, I started my career in 1986. So I completed around 39 years, not 34 as the introduction says. So 90s, I initiated the student to design an expert system. Expert system, a software solution which learns from its previous experience. So the design, even computer design, normally takes hours together. Expert system can, as it can learn from the previous design, new design will take less time. No, that is the idea of expert systems. That all happened. But then the limiting factor was the machine. AI is now into 22, 23, 24, 25, especially on advent of Gen AI tool called ChatGPT. This is because why 2020 is the defining day or year for AI, because by the time NVIDIA succeeded in creating massive chips which can be affordable by Fortune 500 corporations. Why AI 2020? Because appropriate electronics was available, chip was available, semiconductor was available, made available by NVIDIA. Now, other Taiwan Silicon Manufacturing Company, Taiwan Semiconductor Company, AMD, Intel, all these people are also trying now. There's a lot of competition now to create AI chips. 1990, it was mainly academic exercise, limited machine. Now even a laptop, i5, i7 laptop can do lot many things, can process 1 lakh data sets. A single person, a single laptop also can do this with ideally with GPU, NVIDIA GPU. So a lot of technology, new technology, networking, computer networking arrived in 1995. And that created a software called ERP. ERP, Enterprise Resource Planning Software, Enterprise Software, or Supply Chain Software, or CRM Software. All that happened because by the time 1995, there was a matured networking technology. So I am putting in the context. The learners, the students needs to understand the evolutionary process. Nothing happens in vacuum. If you learn the evolution, then you are structurally stable. You can build up very fast. So here it's a big data and modern ML, material discovery and predictive analytics reshape workflows. Another most important is the higher penetration of digital technology computer devices, handsets, mobile sets, social media platforms, cheap devices, computing devices, storage devices, all contributed to the evolution of AI. The cheap data was available, easily accessible data was available to create large language models. So people and enterprises suffer from fear of unknowns, lot of inertia, and initially people will bother about paying, spending in advance, but then that is part of the game. And moreover, the ecosystem is, the business ecosystem, industrial ecosystem is fast changing. Some sector, business sector is smart enough to integrate all this much in advance. So you are living in an ecosystem where lot many people are automating their process and procedures using AI. For you, whether independent of whether you create efficiency or productivity improvement, is a way of life. You cannot be living in isolation. AI is a way of life now. Whether it is the student or teacher or practitioners or companies, obviously it is adding value, it is building efficiencies of all kind. Moreover, it's a way of life. Therefore, I exhort you all to pick up acceleration in integrating understanding. You are not bothered, you are not pained or responsible for adding to the existing body of knowledge in AI. You are asked to use, leverage AI to build efficiencies. For that, you need to be friendly. You need to be at peace with, instead of getting overwrapped. Sometimes the outcomes, whoever experienced LLMs, ChatGPT kind of Gemini, you might be feeling overwrapped, magical, but nothing magical. There is thousands of man years spent on creating these artifacts like LLM or Gen AI, generative AI technology. Now, generative AI is essentially for creating content, whether it is audio, video, or text. The chemical companies are in a position now to create their own GCC, global capability centers, like industrial giants like Amazon, Flipkart, or almost all investment bankers. They are wise enough to create GCC in India because India is offering cost and quality arbitrage. So it's time that German behemoth, Bayer, etc., already might be having, I don't know, the GCC. But at least for marketing, you need not outsource that to foreign ad companies or advertising agencies. You set up a GCC and without much delay, young recruiters can create magical marketing content for chemical companies. It's a huge opportunity. So that GCC can also develop some newer CAD, computer design of process control, quality control. New age, it is existing, but then more efficient solution can be built by this GCC kind of people. Whoever can afford a GCC, better do it fast. 20% of workforce can be from computer, IT, artificial intelligence, data science graduates, or the chemical company can come together. Conglomerate of chemical companies can jointly create a GCC for doing a lot of solution building, software solution building, and also marketing and CRM, customer relationship management. Lot of things can be grouped together. That is the opportunity now. One of the biggest application will be in process engineering. So this literature is from AI. This is AI generated. They say majority of process engineering on adoption of AI can save around 15%. Obviously, predictive maintenance, and also there can be self-configuring control systems, manufacturing systems, self-configuring. So all this is physically possible. Now this self-configuring production system is physically possible, but then whether that is cost-effective or replacement or maintenance on failure or replacement on failure or self-configuring, all three possibilities can be weighed and come to conclusion. But AI can help you to create chemical process equipment designers to create self-configuring wear and tear. It will take care of wear and tear. It can also automatically, by default, without human intervention, can replace some items. Whatever human being carry out in a chemical process industry, majority can be replaced by systems. Now the question is whether it is cost effective, whether the completely automated process engineering shop floor is cost effective or with human being in shop floor. But technologically, a lot of things are possible now. Previously, also a lot of automation took place, was possible. But then here is the end of the spectrum of automation. And in the context, I like to convey one more thing. This generative AI, ChatGPT, Gemini is all old now. People are okay. People are happy with these artifacts to generate content. But then, currently we talk about AI, we talk about agentic AI. Agentic AI is essentially solution building, software solution building, taking cue from continuously energized by LLMs. LLMs are existing. Software solution for a Fortune 500 company or a small and medium scale company will be constantly in conversation with LLMs of the world. And this agentic AI agents are going to be autonomous. Autonomous. You're automating a process with autonomous software entities. Salesforce, no, enterprise software, Salesforce, originally salesforce.com. 3 years back, they invented and practiced integrated agentic AI agents, software agents, like a human being, expert, human expert, autonomous expert. The boardrooms of the industry also can be automated. Agentic AI agent also can replace the CEO or a managing director, or even all the board members can be replaced by agentic systems. That is the opportunity now, this point of time. Indian startups also putting their head or putting a lot of money into this research and development. So going forward, another 2-3 years, a lot of legacy software, including ERP, CRM, will be replaced by agentic solutions. Agentic solutions, multiple agent systems, one agent talk to other agent. No, there is a communication protocol, a series of communication protocol designed and released is available in the marketplace. Chemical engineer needs to understand there is a communication protocol, there is agentic solution, which is going to be autonomous. This much understanding more than sufficient. So like human being, expert, monitoring safety, rule-based sensors, warning alarm, that's fine. But AI-driven mechanisms, systems, no electronic systems, sensors, IoT can be more predictive. Much in advance, it will raise questions, it will alarm, it will sensitize people concerned about imminent failure, risk, accidents. It also facilitates risk management, monitoring, traditional risk assessment. Material is another frontier. Now, literature is available. People are, behemoths are creating new material based upon inputs from AI agents, which is getting all this knowledge from LLMs. LLMs are fed with, trained with, or LLMs already learned all the possible literature available in the world at large. American LLMs are trained in English, but then there are natural language processor which can convert all the available literature from Latin, from Spanish, from German, from Hindi, Polish, Portugal, everything. So it's not that their LLMs are trained with LLM learned only from English literature, digitized English document. It is also learned from other languages through an interpreter, through a translator. A single man understands anything and everything of chemical engineering and material. Iron carbon equilibrium diagram. The child play for LLMs. Now, in the context, I also like to convey one more thing. As I think aloud, there can be a small language model. These large language models are trained with trillions of parameters. Now, there can be language model, there can be electronic brain, which can be trained with, say, 2 billion parameter, 2 billion tokens. So going forward, Chemical Engineers Association, Chemical Manufacturers Association can come together and create a small language model. The teaching entities in the higher education teaching chemical engineering can come together and create a micro language model trained with few million tokens. These are the possibilities. Don't stay away from the massive opportunity evolving this in the domain of AI. Nothing to come out of fear of unknown, come out of inertia, grab the opportunity fast. They say 60% gain. All the current level of bottlenecks in nanomaterial, creating new catalysts, identifying new catalysts, design of polymers. All this can be solved very fast. Only thing is, those who are using these artifacts needs to pay for the licensing fee. But a lot of possibilities. Even in mathematics, even in computer science, even now, we are having a lot of intractable problem. Even the current supercomputer cannot solve in 100 years. That kind of physical problem exists in the world. 100 years supercomputer won't solve some problems. Now going forward, you will get another surprise of quantum computing. Massively costly, even only Google and Amazon kind of people are, IBM kind of people are working on this. They are having some kind of quantum computer. But they could solve some problems which otherwise takes years together in 3 minutes, 2 minutes. Advent of quantum computer is also going to massively change the AI practices. So be ready for another surprise. And by 2030, big Fortune 500 companies and corporations might be possessing quantum computers. May not be pervasive, ubiquitous like normal PCs or even supercomputer. China having maximum supercomputer in the world, not the US. China already having quantum computer embedded missiles and rockets much in advance compared to India. We are catching up fast. So all people concerned also can bother about nation building, can also contribute to the process of nation building. Particle synthesis, even predict polymer properties, optimize catalyst formulations, lot of possibility. Sustainability is a big issue. All the higher education is nudged by regulatory authority to think aloud and sensitize all the participants to bother about sustainability. Every process we design in educational enterprise needs to orient towards achieving, realizing sustainability. Since the AI techniques can help the practitioners to lead towards sustainability issues and energy solutions, energy mix depending upon the geography, depending upon the natural resources available in the geography. AI can help you to design a product mix. How much percentage of nuclear energy, how much hydroelectric. So we need a geography need or consumes 1,000 gigawatt of electricity. That 1,000 gigawatt can be produced by 10% of nuclear, 20% of hydroelectric, 30% by thermal thermal capacity. All this product mix or the possibility of making nuclear energy 40%, all this product mix, depending upon your usage and availability of natural resources, AI can help you without much delay, without much detailed study and analysis. Energy solutions. Pollution control. So the advantage is, human being, even otherwise, even without AI, with the help of digital systems and computer database, can also come out with solutions. But then, at this point of time, heavily relying on LLMs, generative AI models, these pollution controlling models can be easily derived. That's the advantage. Even otherwise, also we are doing it. Now it can be agile, quite agile, everyday basis. Everyday basis, it can model in multiple times. Not a possibility. Because a lot of things are already captured by LLMs. Even live data feeds. So the live data will be put in the context, juxtaposed by already existing database in LLMs. Improvements in renewable energy conversion efficiencies by AI integration. So AI integration, AI technology can be integrated to control, monitor, facilitate. Renewable energy can fetch you 10 to 20% cost. Process industries, which is emitting pollutants, can also start converting that into carbon credits, reprocess, remodel the process involved. They may reduce the emissions, negative emissions, or whether it is carbon monoxide, carbon dioxide, methane, sulfur dioxide. If you can reduce the emissions, especially the low-hanging fruits or sugar industry. Sugar industry can massively reduce emissions if they remodel their process. And that reduction can be converted into carbon credits. Early 90s Kyoto Protocol in Japan, the first of intergovernmental meetings for reduction of emissions. They conceived, the people there conceived idea of carbon emissions, not carbon idea of carbon credits. That carbon credit means, especially developing world can easily come down on reducing carbon emission. And that can be certified by some agency, including international agency. And that can be sold to affluent countries, first world countries who are ready to purchase for compensating their emissions. So that is still there. It is recently revived. The last Glasgow conference or Paris conference, it got revived. In between, it was lying unnoticed without getting practiced, languishing in people's ignorance and apathy. Now it is revived. So every sphere, emission control, emission reduction, enhanced waste management, traditional waste management, massive opportunity here, pharmaceutical industry. The low hanging is drug repurposing. Drug invented for one cause can be used for some other cause. AI-enabled system get easily time-bound analysis, carry out cyber analysis, unlike human being doing it in laboratories, clinical. Drug discovery, molecular design. So electronics labs, electronics, analysis of molecular structure, reactions, atomic structure. The process of molecular design and discovery will be very fast. Drug repurposing, 60%. Clinical trial for new drugs, it can reduce the time required for completing it. Vaccination, etc., it takes months. Even some drugs takes months because it's also intrinsically analyzed. A 360-degree analysis is possible with the help of AI technology. Therefore, even before experiment with human being, clinical trial, you can come to a lot of conclusions. Only thing is that needs to be getting approved from the regulatory authorities. So we a lot of possibilities in fertilizer, pesticide. So we are lacking, India as a country is lacking in micro fertilizer. So we have to buy majority from China. So AI can be used to even overcome the barriers of patents. So a lot of knowledge is in the public domain with LLMs. Using that without violating the patenting rights of other players, people can create new products, new chemical products. Somebody needs to remain focused, that's all. One of the low-hanging fruit is micro-fertilizer. Even some specialized pesticide is not available. So a lot of products can be introduced in the marketplace, created, invented, and produced in the marketplace, produced in the factories and can bring to the marketplace. You need not always, lot of import substitutes are available. Import substitutes can be created without much delay. Somebody should take initiative. Some capital is required. Conglomerate of chemical companies can come together and join together and do a lot of things which can be a massive boost for national economy. Precision agriculture, smart formulations. So there's a lot of automation there, but then a lot of wastage. So AI algorithm can tell you and help you to design nozzles and processors which will be minimizing the wastage. That is all about precision agriculture. Any activity related with agriculture, whether it is removal of weed, maintaining soil moisture, and quantifying the yield, the spread of disease, the accelerated spread of all can be processed by AI machines. AI going forward, it is going to be AI agents. AI in toxicity prediction and risk management. So it's also can replace human being, board member driven strategy formulations. As I said, a lot of replacement can be done by AI systems, agentic AI systems. The ESG practices industry also can be massively influenced by AI systems in appropriate time. The only thing is the AI system needs to be given approval, permission to access databases. Plus, AI system will be continuously fed with IoT devices, sensors. Everyday basis, this AI agent system will be informing, suggesting the management to align with ESG norms. Everyday basis, every hour basis, it can convey. So that's a possibility. So I wish all the participants understand, develop footprints. You need not bother about developing new algorithms. You need to be resourceful and understand this gold rush story. You need not be the original inventor or producer of AI tools. If somebody develop interest in mathematics, statistics, and natural language processing and algorithms, no, can also develop a lot of solutions in AI. But then even otherwise, if you go by your natural calling, majority of you are in chemical engineering, essentially because that is chemical engineering subject is resonate with your body rhythm. But you need not be bonded or constrained by that. If somebody after 3 years develop interest in AI, can go for it. Even otherwise, is an opportunity for wealth creation. Remember this gold rush story. You need not be the original proponent of a particular technology or practice, but you on the sideline after some time can make massive wealth for yourself and for your family and for your enterprise. I wish you all a productive FDP spanning over next 5-6 days, 1 week. And I also congratulate the Department of Chemical Engineering. We were expected to start a PhD program. Mainly, we also decided on the topic to be offered. Yeah, majority of the topics were AI driven, but then there is some delay with the university. This point of time, they modern NEP is essentially aping American new strategies in education sector. But American way of doing is remove minimum barriers, removing almost all barriers. But then here the practitioner, the regulatory authority is not, university is not understanding the spirit. Therefore, delaying the possibility of chemical department starting PhD program. Could have massively contributed had they had given permission for PhD. By this time, minimum 10 students might be working on AI-driven processes in chemical engineering. That is not disappointing. That has happened. Going forward, people can change. Establishment can change. So we are hoping for a better world, better practice, better understanding from regulators and all the players involved. I thank you all. Wish you a great day today. Thank you.
Thank you very much, sir, for your encouraging and insightful address on the areas in process engineering sector where there is a possibility to integrate AI. Your vision and leadership truly inspire us to continuously upgrade our knowledge and embrace new technologies like AI for academic and professional excellence. And sir, I am really sorry for mistake I made in stating your year of experience. Here I would also like
year of experience 39 and number of
Yes, sir.
PhD is all old. Number of PhD 27.
Okay, sir. Thank you so much
27
for clarifying.
PhD scholars completed PhD under me.
Okay. I would also like to add to this that it was indeed sir's idea to keep the topic of this FTP as AI in chemical engineering instead of previously thought other topics. And sir, we really got very overwhelming response. So thank you once again, sir.
Okay, okay. Thank you.
Participants, we are extremely fortunate to have an eminent guest speaker with us today who will be delivering the expert lecture on application of AI in the field of chemical engineering. But before we begin the guest lecture, I'll take a short technical break of 2 minutes and hand over the session to Dr. Ramesh Bhande, sir. Please stay connected and rejoin the session promptly after the short 2-minute break.
Good morning, sir. Good morning, Professor Gudi.
Good morning. Good morning,
good
Professor Nita. Yeah. Can you hear me?
Yeah.
Yes, sir.
Hello, sir.
Yeah. Good morning to everyone. Yeah.
Sir. So, respected principal, so we'll start introductions of the sir first. So, respected principal, head of the department, distinguished speakers, and esteemed faculty members and dear participants. Good morning to all of you, to everyone. It is given me great pleasure to welcome you all for this faculty development program. Today's session is truly special as we have with a highly accomplished academician, researchers, administrator, whose contribution to teaching, research, institutional developments are truly inspiring. We are honored to have Dr. Ravindra Gudi, Professor in the Department of Chemical Engineering at the Indian Institute of Technology, Bombay, as our resource person for this session. Professor Gudi obtained his BTech and MTech in Chemical Engineering from IIT Bombay and earned his PhD from the University of Alberta, Canada. He has been associated with the IIT Bombay since 1995 and had made significant contribution in the academic, research, and leadership. He has held several important administrative positions, including head of the department, dean of alumni corporate relations, and professor in charge of the IIT Bombay Research Park Foundation. Currently, he serves as a AI and machine learning chair professor and deputy director, finance, infrastructure, and administration at IIT Bombay. His research interests include process system engineering, modeling optimization, process control, fault diagnosis, sustainability, green engineering, and applications of artificial intelligence and machine learning in the chemical engineering. He has published more than 150 research papers and hold multiple US patents. Professor Gudi has fellow of Indian National Academy of Engineering and Indian Academy of Science and IICHE and has received several prestigious awards for his academic excellence and contribution to industry-academia collaboration. We are confident that today's session will be the highly enriching and insightful of all participants. With these words, I warmly welcome Professor Ravindra Gudi and invite him to deliver his address. Thank you. Over to you, sir. Sir Gudi, sir.
Thank you very much. Good morning. It's really a pleasure to connect up with the extended fraternity of chemical engineering in this very important FDP related to AI. There is a lot of exciting developments, exciting opportunities in the area of AI, as Dr. Thampi has as well presented in his inaugural address. There is substantial value that one can generate in accelerating the pace of technology as we foray into various themes in chemical engineering. And what I'll try and do is bring in some of the facets of AI. But as we go ahead, I would like to suggest and propose a very balanced approach to how we adopt AI. Current approaches seem to be focused on looking at AI and completely data-based or data-driven approaches to AI with significant emphasis on the quality of data and the like. But I would also like to, at the end of my talk, leave you with a message that, of course, AI as known, artificial intelligence, machine learning, while these are great facilitators towards our research, I would like to leave all of us with a common focus that we would like to develop, which is AI as in augmented intelligence. That is, don't forget your domain knowledge. Domain knowledge has a very, very strong role to play in improving the overall quality of AI models. And that's something that we should perhaps keep in mind and try to bring in as we make AI as a strong facilitator in everything that we do. So let me share my presentation and begin our discussions this morning. I'm not able to see the share button here. Oh, yeah, it's there. Yeah, I'm able to see it. Let me share the entire, sorry, I should probably stop sharing and share my entire screen so that it's, yeah, that's correct. Yeah. Okay, all right. So I have kind of taken the liberty of slightly altering the title of my presentation. I hope all of you can see this. If one of you can confirm, please, that
Yes,
you can
sir.
see
Yes,
this.
sir. It is
Yes.
visible.
Okay. Thank you. So I have titled it as Whether AI. Whether AI is essentially trying to pose a question to you whether AI is um, enabling all the promise that it's supposed to, or whether we need to do a lot more with AI. And I'll paint quite a few applications in the chemical process industry as we go ahead. Um, so let me begin with a very simple illustration of what AI is all about. Um, and what role it can play in kind of advancing the current scheme of things, the current industrial practices that we have in systems engineering. This example is a very simple example of a boiler application where you have fuel that is fired in the boiler and you have potentially a flame that's generated that impinges on the boiler tubes. This basically is fed with water, which gets converted to steam. The steam drives a turbine, and that generates power. And in all of these typical applications, what we would like to do is maximize efficiencies, be it in manufacturing, be it in pharma manufacturing, oil and gas, what have you. You want to maximize efficiencies. And if you want to really do that, in the context of the combustion, you want to eventually generate a high efficiency combustion, which is what I have indicated in the green at the bottom of the slide. So you want AI to step in over and above what we are currently doing to be able to be a facilitator in maximizing the efficiency of combustion for this application. So what all do we need for that? Obviously, for AI, you need data. But what I'm going to suggest to you is you also need models. So let's assume that we have a lot of data. Where are you going to generate that data from? You're going to generate it from various sensors that you would deploy around the application. The first one would be the fuel quality sensor. The fuel quality typically is measured maybe once a shift or maybe a few hours frequency in a day. And you would send this to a lab and you have the assessment of the fuel quality. Then when a flame burns, you have a hissing sound frequency. So you could basically sense that using acoustic sensors, it give you frequency information of how a flame burns. Then we could have thermal sensors that in a sense give us the losses. These are deployed all across around the flame just to make sure that we can maximize or get a sense of what the temperature and in the environment is. Then the point of action obviously is the flame. Now the flame is a very, very tricky disposition, I would say, has a very tricky disposition. A flame can dart, a flame can shrink, a flame can be of variable volume, a flame can flicker, so it can have different frequencies of flicker. Color can be different. It can be, for example, orange as you see here. It could be blue, which is more indicative of green burning. So it can vary in color as well. And what we want to do is basically at this point of action, you want to qualify the health of the flame, if I may, and you want to basically have a clean burning flame. Clean burning typically would be bluish in nature. We would like to maximize that. We would like to minimize the flicker. We would like to keep the volume as consistent as possible so that a large area of the tube is covered, the boiler tubes are covered. You want to make sure that the air to fuel ratio, the primary air staging, the secondary air staging is all done in an appropriate manner so that it contributes to all of these attributes of the flame health. And this is directly measured through flame images. So you could have, let's say, a 120 degree apart placement of these flame cameras that can sense and generate, a qualification of the flame health. Then you have emission information, which also talks about Sorry, is there a question? There is, maybe if everybody can mute if there is no question. Yeah, request if everybody can mute or the moderator can mute everyone, please, except me. There is a bit of a
Yes, sir,
talk.
I will do it. Okay.
Yes, please. Thank you. So there is also emission information, which gives us a sense of the, partially burnt or the unburnt fuel in the emitted gases. So all of these sensors typically give us data that can help in assessing the health of the combustion. Now we have a fuel quality sensor. So, these sensors basically talk about the 4 V's that we understand in data attributes. One of them is, of course, the volume of the data. And by volume, I mean the volume of archived data that has a wealth of knowledge about various characteristics of the flame. So first V is the volume. The second V is the velocity. Velocity is the rate at which they are streaming when you collect data. For example, the flame images are streamed at several frames per second. The fuel quality sensor is streamed relatively at a slower rate, maybe once a shift. Acoustic sensors give us frequency information. The thermal sensors give us information about, in terms of the thermal environment at a relatively faster frequency. Emission gives us on terms of the composition. So there is a lot of data that's coming at different speeds. So velocity is the second attribute. First is volume, second is velocity. The third is the variety. As you can see here, you have flame images, you have frequency information, you have thermal temperature information. So the variety of data. The fourth V is the veracity. Veracity has to do with the accuracy or the variability, and a lot of, depending on what kind of sensors you deploy, you can basically have velocity that's, the veracity, which is, depending on the sensor accuracy and the like. So all of these 4 V's, the volume, the variety, the velocity, and the veracity, contribute to the fifth V, which is the the value that this data brings in. Now let's assume that we have some way of fusing this information with all its different attributes and the like into the brown box, which I've called as the combustion quality assessment. Now here is where you have all the data, and here is where AI as an artificial intelligence can step in to kind of assess the quality of the combustion as it is happening at the current point in time. Now, what does this assessment entail? It basically entails 2 steps. One is generating a metric that represents the health of the combustion. And that metric can be, for instance, the related to the efficiency, which says, okay, out of the total amount of fuel that's fired in, here is the amount of power that is generated. So that is the current indication. Now, this assessment is done using AI and ML through various ML approaches as well as some AI approaches, which we'll talk about a little later. ML approaches typically are advanced statistics-based approaches that give us a sense of that metric, which is the amount of fuel that's converted to power. But where does AI step in? AI basically steps in terms of looking at the archived data. There is huge volume of archived data that has been already implemented in the past. They can be classified in terms of good, bad, and ugly regions of operation. Now, when you have this classification of good, bad, and ugly in the archived data in the past, you can compare the current operation with respect to that past operation. What does that mean? That means that the past operation has certain attributes as well as the bad actor, information about the bad actors and the good actors in terms of the profiles or templates. So, for example, there will be a certain template of variables associated with the golden region of operation. There could be a certain set of templates or profiles associated with average. And there could be certain templates associated with the ugly or the bad. So if we want to be able to classify the huge volumes of data in there and classify that data into good, bad, and ugly and the appropriate profiles and templates, what we could do is assess the current combustion quality relative to those templates and be able to qualify or quantify the current combustion as good, bad, or ugly, but on a continuum scale. It's not just a discrete saying it's good, it's bad, or it's ugly, or it's average. It's not just the qualification of that, it's also quantification in terms of how good or how bad or how close it is to the golden operation. That's something that the combustion quality assessment step needs to do. And here there is a very, very rich role for AI and ML to play when we are performing this qualification. The next is, we need to ask the question that, okay, now we know relative to the best seen operation, where is the current operation? What do you do to take it to the best seen operation, right? One possibility is you use a combustion system model. In modern day AI and ML parlance, this is being called as a digital twin. The question is, how do you build a digital twin? As the name suggests, a digital twin is a twin of what is actually happening in the plant. So what do you need for that? You need to reconcile a system model to be able to represent the current scheme of operations. So you basically need to use the current data to update, if it is not already accurate, update the system model to be able to be representative of the current region of operation. So a digital twin model has to be built. And this digital twin, which I show in a very simplified form as a combustion system model, it advises what steps. So how does it advise? It uses advanced optimization and control algorithms. It advises on what could take the current operation as close to the golden operation batch as possible, or golden operation as possible. So that's the role of a digital twin, where again AI and ML role can play in building the digital twin to be able to represent or replicate the current region of operation. And then, of course, as I said, it's guided by advanced optimization and control tools, which basically are now becoming closer to reality or realizing their rich potential simply because of the advances in computing infrastructure, advances in sensing infrastructure, and the like. These tools are now becoming closer to realizing their full potential, and by applying through the query approach of querying the digital twin, looking at the signatures of the good, bad, and ugly operations to the quality assessment step, these three brown boxes together help us to exploit the full potential of AI and ML algorithms to be able to realize what I show as high efficiency combustion. Now, this is talking about AI and ML and what those algorithms are. As we go ahead, I will paint some of them, but it's important to understand one very key message here, and that is that all of these approaches cannot work only with data, because data is only what you can operate in the current region or archived in the past operations. Does AI and ML based on data alone help us to realize what has not been seen in the data? And that's where the role of a very, very well-tuned digital twin comes in. And a digital twin basically represents domain knowledge or engineering, mechanics, or physics of the system. It represents that physics combined with data makes the AI and ML model, the resultant AI and model, which I loosely refer to as a digital twin. That is something that is physics plus data. So it's augmented intelligence, if I may call it. And this augmented intelligence can help us to improve the quality of our models, improve quality of our predictions, and be able to realize a kind of a operation that perhaps has not been seen before, and that can help us to push the benchmarks in terms of being able to realize higher and higher efficiencies. What you can do in combustion quality assessment is to compare with the known best seen efficiencies. But how do you know? For example, if in the archive data, the best seen efficiency of operation is only, let's say, 40% in terms of the conversion of energy to power, I would say that querying through a digital twin or a first principles mechanistic model that is well tuned to the current operation can actually help you to explore opportunities beyond what is best seen in the archives, right? So that's where you need to re-establish your benchmarks and see whether we can go for a relatively higher efficiency, which, the full potential can be realized through the use of augmented intelligence over and above AI and right. So that's the message I want to kind of all of us to work towards, which is how do we bring in the first principles knowledge and make sure that this can help us realize the full potential. Okay. So let me go to the next slide here. I hope the slide transition is visible. If it is, can somebody confirm the
Yes,
slide
yes, sir.
transition?
Yes, sir. It
Thank
is
you.
visible. It is visible.
Thank you very much. So I'll just talk about the role of digitalization, which has now spurred this growth in AI and ML and its potential. Of course, we all know digitalization as digitizing and then digitalizing the data. What has spurred its growth, advances in computing, sensing, communications, platforms, all of this. And, together it brings in an impact of increased connectedness between various elements. Let's say in chemical engineering, we have a large plant, different aspects of how do we bring connectedness in decision making, integration of the decisions, promoting safety, productivity, as well as, together all of this realizes OPEX, which is operational excellence. I think we are in a realm where we are going into from IoT to IIoT, of course, and they're looking at various standards, Industry 4.0, Industry 5.0, and so on. And just briefly talk about that. Look at operational excellence. What does it entail? And then look at what is AI and big data in the context of industrial practices. Look at different scenarios for AI and data analytics, particularly emphasizing the role of physics in knowledge representation. A few case studies and then the summary. Very quickly, digitalization. It's basically science and technology-based business transformation that looks at transforming conventional or partially digitized approaches to bring in business advancement, decision-making. Of course, it promotes improved connectedness between different entities, promotes safety, compliance, improved productivity. So in a broad sense, science and technology based generation, transformation and analysis of data and information is what digitalization is all about. The steps would be digitalizing, and then using the digital information to do advanced decision making for deployment. That's the digital transformation we're talking about. What has spurred it? It really has been spurred by several and I'm presenting only 4 of them here. This is basically looking at advances in sensing technology. So, the sensors are becoming now a lot more multifunctional and powerful in terms of the sensing principles, the ability to self-calibrate and diagnose themselves. They can communicate, they can be at the point of action and communicate what's happening there. And now the cost is also decreasing rather. Increasingly becoming more affordable. So advances in sensing technology, computational advances, okay, I'll come to that at the end, but networking and communication, the rise of 5G, which promotes real-time analysis, low power consumption, again, factor of cost, and of course the mobility, so they can actually be deployed at the point of action. We have seen a very particular application where in a wiped film evaporator, where in the annulus area, you want to sense the temperature. Temperature sensors can become as miniature as that in the face of the white film and be able to transmit what the temperatures are to prevent that at no point in time, especially when you are processing thermally sensitive materials, the temperature should not exceed a particular threshold. That kind of application is also possible. Then, of course, we have computational advances in terms of powerful algorithms, optimization and control, which I think the chemical engineering community is very well familiar with. And then, of course, we have the platform infrastructure with IoT operating systems, cloud and edge architectures, decentralized edge computing, blockchain to ensure safety and security of the data. So all of this together has created a digital transformation, and this has helped us to better be positioned to leverage the promise that AI and ML has to offer. Quickly about IoT, industrial IoT, Industry 4.0. Basically, it helps us to achieve, but actually even redesign benchmarks. As I talked earlier, it can, together with digital twin, it can actually help you to advance your benchmarks. It, of course, gives you good performance in terms of safety, productivity, and operational cost by monitoring value additions in real time. If I have, let's say, a value chain in our industrial manufacturing, we want to make sure that at no point in the chain we have a decrease in value. So monitoring value additions in real time, coordinated management and controlling of industrial processes, safety, assets in operational time, elevated security levels, both in terms of data as well as operations, reliable communication for industrial and high integrity industrial environments. A case in point is, for example, a nuclear reactor or FCC. But also, if you look at lateral applications, for instance, in aerospace industry and the like, drones, you want to make sure that the communication is very reliable. So going towards Industry 4.0, 5.0, and a wish list for 6.0, we really have a lot of promise that is there that facilitates the realization of AI potential. So advancing CPS, all of this is something that we are looking at. Okay, what is the impact it brings? Suppose I have said this already. It basically brings us improved connectedness, integration, safety, productivity, and all of this above contributes to operational excellence. I'll share these slides, just go a little fast in the interest of time. Okay, so let's come to AI, as in AI applied in chemical engineering. We are talking about the AI being a discovery and purposeful utilization of meaningful patterns and information in the data. What does this mean? You have the four V's of data. You want to basically delve into the data and see what AI can help with. But the important
Sir, you are not audible now. Hello.
Hello, is everybody with me? We lost connection for a while.
Yes. Sir, now you are
Can you
audible.
see my screen? Can you see my screen?
That is on hold. Now it is
Screen
visible.
is on. Now
Yes,
it is
it is
visible. Okay.
Yeah. Okay.
Okay. Sorry about that. Some networking. We are talking of networking using digitalization, but we had unfortunately a drop in communication. Anyway, coming back. It's important to realize that physics has a very, very strong role to play in augmented intelligence. So this AI that you see here is artificial intelligence, but we want to transform it or repurpose it or recoin it as augmented intelligence. Physics has a very strong role to play, which we are not adequately exploiting. At the faster scale, we have always been doing process control in chemical engineering. But can we do more? For example, nonlinear model predictive control. Model predictive control is purely data-based. To realize the full potential of control, nonlinear model predictive control has come up. Nonlinear model predictive control has to bring in the kind of first principles physics to be able to realize the full potential. Now we are talking of data analytics when you're using only pure data. So there you have data to information, information to knowledge, knowledge to wisdom, the kind of distilling that needs to happen, like in a conventional distillation column. By distilling, I mean, you basically want to make sure that you are refining and delving into the knowledge that is present in the data and converting it into wisdom. Now, there's an important role of physics in this knowledge representation that needs to augment what you do with the data. And that's something I'll come up in a little while. Here is typically the knowledge pyramid. We're talking of discrete elements that form the data and give you a sense of the raw pulse of the system. You aggregate the data of the raw pulse. You have information in terms of signatures and trends. You augment you kind of organize the information and you get knowledge in terms of best operation templates that I talked about in the boiler application. And when you apply this knowledge across different boiler plants, across different regimes of the boiler operation, maybe a high pressure steam, average pressure steam, mid pressure steam, low pressure steam, when you're generating all of these, when you apply this knowledge, you get consistency in best practices. So from an AI perspective, the message is that you have to listen carefully to your data. Certainly, listening carefully to your data gives you all of these benefits, but I must add that physics must step in to improve the quality of the models. And that essentially brings us to this slide, which talks of what is it that we can do in knowledge representation for AI. We want to make sure that you use all sources of knowledge. Data is only one of them. You have the physics, which is the second, right? It's very, very deep in terms of when people are talking about deep learning. But you need to look at deep learning not only in the context of the advanced architectures that are being used for learning from the data, but you also need to bring in the deep in the context of knowledge that can be represented in some of these architectures. So models is one, which is the first principles physics. Measurements is the second, which is the data that conventional AI approaches use. The third is that you should not ignore the fact that you actually know how accurate the data is and how accurate the model is. We talked about one of the V's as veracity, which is the sense of accuracy in the data. So let's not forget that we do have a sense of what is the extent of mismatch of the models or what is the noise in the measurements. That's also a source of knowledge that helps us. How does it help us? It helps us in being able to weigh relatively which model. If a model is more accurate in the data, I will weigh that in a prediction better than the other, and so on. So it helps us to make those kind of decisions. Okay. Now, let's come back to chemical engineering. What have we been doing from these three sources of information? The data reconciliation that you see here as the first row is actually been already close to 4 decades of research and now seeing a lot of application in the industry where you assume that the model is accurate. Typically a mass balance. Nobody can question a mass balance, right? A model is accurate, mass balance model is accurate. The measurements that are generated are noisy. Now, can we have a digital twin, if I may use that phrase in model parlance? Can I have a more refined set of measurements that are reconciled with the digital twin, which we assume that it's a perfect digital twin because we have assumed that the model is accurate. So data reconciliation is one of the approaches that we have been conventionally doing in chemical engineering. The second row represents if I have a model that is noisy and the measurements that are also noisy, but two sources of truth, apparently noisy, can improve our reconstruction of the truth. And there is a lot of research that's happening in estimation and filtering, some of them also seeing applications. For example, the most rudimentary amongst them being the Kalman filtering, but the advanced variants of that in terms of particle filtering, moving horizon estimators and all of that. A lot of advances are already being published in literature and also seeing the light of the day in terms of applications. The third is, of course, your model, if it is in a sense not perfect, and we talked of a noisy model, but we also talk about, empiricizing some aspects of the model that is not known, which brings us to the gray box models and adaptation of that. That's something also that has been quite well broached into, especially in applications like pharma or polymerization, where it's hard to predict the reaction kinetics, but you can empiricize and learn that empirical model by adaptation. That has increasingly now getting into practice. And the last one is, of course, when I have absolutely no model, first principles I don't have or pretend that I don't have, and I have lots of data. This could be noisy, and that's where the current AI is, but it has to advance into the upper three rows. Black box modeling, multivariate statistics are well-known. ML approaches, ANN getting into deep learning is one of the advanced AI algorithms, fuzzy and fuzzy classification, AI tools, all of these fuzzy reasoning methods are increasingly getting popular now. So this is kind of a broad spectrum of what we know in chemical engineering and what we have applied in chemical engineering, but we need to advance this further by bringing in physics a little more strong. Okay. Now let me pause here and see whether there are any questions before I get into a little bit of the detail. Any questions up to this point, please? Any questions? Okay. All right. There are no questions. Let me go ahead First, let me tell you about analytics and the role that AI has played, typical objectives. For example, the simplest could be that I have an inflated measurement through various sensors that I have deployed. Can I understand and do data reduction, dimensional reduction of that measurement space to understand more and simplify the task of, for example, monitoring. Okay. The other is discovering patterns and clusters in the data. We talked about the boiler application. There can be regions when the boiler is completely burning with a orange image for some reason or the other. Maybe the fuel quality is not good, or the primary air staging, secondary air staging is not appropriate, air to fuel ratio is not good. There are different, the regions of operation where the flame is appearing orange. And that's one cluster of data. It could be that a very expert operator, the color of the flame is blue. It's a high efficiency operation. That's a third cluster of data. So how do I delve into the huge volumes of data and discover these clusters and associate patterns with them so that I'm able to generate those signatures? So that is the second AI. The third is what I cannot sense, what I want to really control or monitor. If I cannot sense that, I can build a soft sensor. Now, the soft sensors are now increasingly getting in practice for polymer quality or, the pharma, the concentrations of the product and so on, which I cannot measure directly due to various constraints. So soft sensors. And likewise, for closed loop control, I could generate reduced variance estimates, predictive models for prognostics. I'll show you an application where physics has helped. Likewise for diagnostics, detecting the bad actors. And then, of course, there is this aspect of GMP, good manufacturing practices that tell us that you need to continuously look at leveraging both the data and the first principles models to be able to continuously make this improvement in decisions. And that continuous performance assessment, grading the performance and ensuring compliance is something that AI can typically help. It's one of the objectives of AI. Very quickly, what are the challenges in analyzing the data? You have a design problem where you want to make sure that you generate informative knowledge. What does that mean? Locating your sensors, designing the sensor networks. There's a lot of research that's happening in the IIT Bombay. Also, my colleague Prachamani Bhushan, there's a lot of work in that area. How do you transform and visualize the data to detect outliers, nonlinear effects? How do you present the data in a form suitable for analysis? For example, when you're doing, let's say, visual analytics and the like, streaming, aggregated, federated, depending on who should see what kind of data. That's more of a design problem. And the second is the analysis problem where AI can step in. AI can step in here in the design problem as well, but also in the analysis problem, looking at various attributes of the data, such as size, collinearity, heterogeneity, nonlinearity, low signal to noise ratio, different classes of data. And of course, how do you complement modeling knowledge with appropriate relative importance? So here is just a quick look at, what we talk about is a system, operating system, where the causes are hopefully deterministic. Most of the time they are, because these are decisions that are propagated through the control systems of, different industry grade control systems. So hopefully the causes are deterministic, the effects are measured, and you have disturbances and drifts in an operating scenario. An abstraction of this is this, which is basically the causes are deterministic, the effects are predicted using a model, and hopefully you have captured the individual or an aggregated form of the disturbances through the model. And this is what one has to deal with when we're looking at digital twins and the like. We, of course, never know what the ground truth is. We are trying to reconstruct the ground truth that is there in this green envelope. What we want to do is see how AI and ML can help us in reconstructing as close an estimate of the ground truth as possible. So to be able to do that, you have, of course, different attributes of the data, the relationship that you want to do. They could be nonlinear, time varying, various things can happen. Data is, of course, viewed as in a matrix X. R m cross n, m is the number of samples, n is the number of variables, and you want to basically delve into this both in the archived as well as the current data to be able to make sense of what you're getting. I'll skip this slide. I did talk about this, but basically what we're talking about is a white, gray, and black box model. The next slide shows that a white box model to the extent that we can develop. So uses first principles knowledge and data to update the parameters. It gives you a white box model. Gray box model, I talked about this, and then the black box model. But let me get into, as a continuation from here, let me get into what are the representative problems that we can solve. The first is, of course, I talked about data reconciliation, compression, clustering, regression, performance characterization, model plan mismatch detection, and interaction and nonlinearity detection. Let's look at each of those. Okay, this is very well known for those of you who are not oriented to data reconciliation. What I have is a process model, like I have a mass balance. I have raw measurements that come from, let's say, meters that I implemented in the field. And what I want to do is these raw measurements will never obey the process model because of the noise present in them. So how do I correct these raw measurements to align with the process model so that I get reconciled measurements based on which I can make decisions? I can't make decisions based on raw measurements. For example, if I want to determine efficiencies, efficiency is the total power produced divided by total energy locked in the fuel for the boiler application. Now, if I look at the power meters, and if I look at the total fuel flow and the energy associated with the fuel going in, and take the ratio of that, I can never get a sense of the actual efficiencies because these are noisy measurements. So I want to reconcile them in some sense. In the simplest case, let's say if I have, let's say natural gas that is transferred across the exploration and production plant to, let's say, an LNG processing plant. So there is a plant boundary between them, right? So upstream, the exploration and production has a meter that says, I have transferred so many million standard cubic feet of gas to the LNG plant. The LNG plant liquefies that. Now, LNG plant at the plant boundary has another meter that it uses to determine how much gas it has received from an upstream unit. Now, since there are 2 meters across the boundary, one on the upstream side, one on the downstream side, this 2 meters will obviously never agree because of the noise bias, etc., whatever is there. Now, how do I generate an estimate of the actual gas that is transferred from the upstream to the downstream? To be able to do that, because that's money, you see, the downstream has to pay the upstream. If I have to get a very reliable estimate of that, I need to use data reconciliation that is based on a mass balance. And this mass balance can help you to reconcile the measurement from the 2 meters and check for biases, check for gross errors and all of that, and be able to get a sense of the actual. So this is typically what they call as a custody transfer problem between 2 enterprises. The same thing can happen in oil and gas distribution networks where oil is dispensed into tankers, gas is dispensed into pipelines. You want to make sure that you get a sense of how much is the mass that has been transferred, to get a sense of the revenue transfer and the like. So those are some of the applications of data reconciliation, which has already been well known, adopted now in the industry, but this is one of the simplest applications of ML. The second is revealing the lower dimension subspace. As I said, you have an artificially inflated space. You want to make sure that you get a sense of what is the lower dimension space. Sometimes, you have, a lot of measurements. And here is one example of that. I have the standard Tennessee Eastman problem, which has 52 measurements across the plant. This is a contrived problem, though. In an actual plant, the inflated space can be much, much larger. Okay. Here are several units here, and this is a benchmark that's been used for testing various, prognosis, diagnostics, advanced control, all of those applications. Now, one could take these 52 measurements in all of these and try to see, because the 52 measurements are in the inflated space, can I get a sense of the lower dimension, what is happening, so that I can make smarter decisions? So one of the simplest ML algorithms that has been well tested in literature is what they call as PCA, which is Principal Components Analysis. that basically what it does is it looks at the 52 measurements, looks at the variance matrix that you generate from that, decompose that variance matrix and try to extract the information out of that. And then along from the 52 measurements, you generate, let's say, linear combinations. In this case, I show you 15 such linear combinations in the first column. These try to represent the variance that is there in the data that we can use from the 52 variables in several samples. Now, based on that, you try to reconstruct the truth. There is a measurement of how much you have reconstructed. That is what they call as percentage variance captured. And as you can see from there, the 15 linear combinations capture about 64% of the total variance present in the data. Is that adequate? Maybe, maybe not. How do we try to capture the complete variance in as fewer dimensions as possible? That's a challenge problem in the literature. Here, this shortage of about 37% could be because the data has a lot of non-linearities. It could have dynamics in it, and a linear combination of only the point samples may not necessarily represent the entire variation and information in the data. So variants to this PCA, dynamic PCA, and there are several variants of that. One of the other advanced algorithms is also what is called as correspondence analysis. Now, correspondence analysis uses different metric of the information. It uses something called inertia in that. And if you look at that, sorry about this, distortion of the titles here. But if you look at it for the same plot, the same number of dimensions or linear combinations, 15, CA does a better job of being able to explain the information. It captures about 96 to 97% of the total information present in the data through a metric called inertia. And this can be proposed as an improved algorithm or PCA, but again, not quite so. Because, you need to see what is the objective of PCA. You need to see what's the objective of correspondence analysis. And there, the way the objective function is formulated and the like, and the intent of using these algorithms can be different. And so PCA could be adequate in some cases, but in some other cases you might need CA. But here is a suite of algorithms that can actually help you to basically determine for an end objective that you have, what is an appropriate algorithm. I'm just showing you two of those here. Okay. Let's look at the objective of fault diagnosis incorporating physics. And I've used the simplest of the algorithms, principal components analysis, PCA here. But here is an example of how we can bring in first principles knowledge to augment what PCA can do, okay, in the area of fault detection and diagnosis. This is some of the work that we jointly did with the Computer Process Control Group at Alberta. The objective is that we have the application at hand, which is LDPE production, low density polyethylene, which, as we all know, is a polymerization reaction of ethylene going to polyethylene. Operating conditions are temperature about 150, pressure, very high pressure, 1200 atmospheres, and the degree of polymerization that is 10,000. Now, it's quite all right if we only have this reaction that is happening. But as it turns out, ethylene can also decompose into carbon and hydrogen. It can also reform itself to form methane and hydrogen. Now, while these have the problems of lower yields, that is, I have quantified that as economic loss, lower yields in terms of LDPE production, side reactions are there. There is also aspect of safety, high exothermicity and a potential explosive reaction because of hydrogen and methane. So what you want to be able to do is make sure that this hotspot does not get formed at any point in the reactor. And you want to basically predict the hotspot formation if it forms relatively early so that you can take corrective action. Okay. So how do we do this? One is you can use principal components analysis to represent what is the normal operation based only on data. And then say that anything that is an aberrant outside of this template of normal operation is an abnormal operation which you can potentially initiate remedial action. But here what we do is we do something more. We say that let's write an energy balance equation. This energy balance equation says that heat input which is coming through feed gas and the initiators, and the heat output plus the heat of heating related to heating is something that should close to zero. A simple energy balance equation. Can we use this along with the data and principal components? Yes. Why? Because there is a certain uncertainty associated with the specific heat dependence on temperature that goes into these terms here. Okay. Now, since we don't know that, we want to write this equation in a different form. We basically write this as an energy balance with separating the terms of temperature and specific heat, and the deterministic terms are in H1, H2, Hi, which are functions of temperature, and the alphas contain the uncertainty elements. And this is a classic equation where PCA can step in. I said PCA could help here. PCA can step in because really what you're doing is you're putting this H in a matrix, all the H's which are dependent on temperature, and you're estimating the alphas. So if you perform a PCA on the H's, you can basically establish the limits of shape of operation, the templates of shape operation, and then any operation that is violating this can actually be detected as an abnormal operation. As a quick case study, here is the discussion over here. You want the closure error to lie within these limits. It's quite so till about 5,000 sampling instance. At this point in time, something abnormal happens and there is a runaway reaction. It violates the templates. Detecting that early is possible, about 3 minutes early as compared to traditional database methods, because the physics has come in and now we are able to detect 3 minutes early that there is an onset of decomposition, which can help in initiating remedial measures to prevent this from happening. Okay. So this is the second application of just give me a minute here. There's somebody trying to reach me. Okay. Okay. We'll talk about the data clustering problem. And here what we are talking about, for instance, fault detection and diagnosis, nonlinear identification. But basically the idea is that, in the huge volumes of data, we are basically looking at, delving into the data and trying to find out the classes of data where, for example, a high efficiency operation, average efficiency, how do we do that? Finding a structure in the huge amounts of data that we look at. There are a few lateral applications, talked about fault detection and diagnosis, regression, but systems biology in healthcare, identification for process control, all of these are important. So the clustering problem is basically trying to look at dealing with different types of data attributes, discovering clusters with arbitrary shape and size. Hopefully they should be resolved so that they don't have an overlap. Otherwise you have a difficulty in decision making. They should deal with noise and outliers, accommodate a high dimensionality and so on. While we say that minimal requirements for domain knowledge, it's good to incorporate as much knowledge we have. And then the clusters must be interpretable, usable. So several approaches in AI that help you to clustering. One is hierarchical clustering, which could be agglomerative or divisive. Agglomerative is you take one data point at a time and agglomerate them. Divisive is you take all the data together and start dividing them based on some metric. So that's one of them. Second is exclusive through algorithmic approaches, k-means, or a fuzzy variant of that, which is fuzzy c-means. And then mixture of Gaussians, which is probabilistic clustering. Several advanced approaches beyond these also have been proposed. Here is one, simple transformation of the data that we have tried out, first published in Ding et al. 2001. Now this is, there are two clusters in the data, which when I present in a two-dimensional plane in the upper plot, shows that one of them is a blue cluster, one of them is a red cluster. Okay. And when I plot it as raw data, as you can see, there is an overlap. Now, suppose I have a new data point that comes in and I want to find out whether it is red or blue. If it projects anywhere here, if you can see the cursor, or anywhere here, if you can see the cursor, that decision is pretty obvious. But if it falls in the overlapping region here, I wouldn't know whether it's a blue or a red cluster, right? I would preferably like to have these two clusters as resolved as possible. Okay. Now, what does that mean? That means that the red cluster has a center and the blue cluster has a center. I want to move the centers as apart as possible. There are also the data, the raw data has a significant spread, as you can see here. They're not perfect rings, crisp rings, they are diffused rings. So I want to separate the centers and I want to compress the data. To be able to do that, what I can do is use advanced algorithms to basically create what I see as a lower plot. In the lower plot, you see that the thickness of the rings is also reduced and the centers are separated. Okay. How have I done this? I have done this to several nonlinear transformations. This is the transform space as opposed to the raw space that I see in the upper plot. Now, if I have a new data point that comes in, which I know is blue, I can very crisply classify that as blue instead of red because the clusters are separated. So what I do, I take that new data point, make it go through the same nonlinear transformations that I did when I separated these two clusters, and then project it in the new space. I'm able to get a very clear resolution, right? So don't we want to do that for all the data? Yes. But are the AI algorithms very powerful enough? Mostly so, but there's still a lot to do to be able to resolve these clusters. So when I cannot resolve these clusters as crisply as you see here, I do need to look at fuzzy clustering. I need to accommodate the overlaps and I want to help in the decision making. Here is a second example of, the one from in the healthcare area that looks at different types of cancer treatment. When I look at diagnostics, there could be different types of cancer that you see in, could be large beta cell lymphoma, active blood, B, follicular lymphoma, and the like. In the raw space, you look that there is an overlap, but in the transform space, you see that they are particularly resolved. As you can see here, the purple stars all get agglomerated into a single star. So this is a crisp cluster in the transform space. So things like this is something that we could do to basically look at how do we do the classification step. But closer to chemical engineering, we could look at basically the advanced control of high purity distillation columns, where the overall operation can be classified into 4 clusters, linear clusters, and you could schedule the controllers in such a way that you get high and a good control of the high purity distillation column. This is typically what we try to do in multimodal control, where we deploy the appropriate model that we use in the controller design through a fuzzy switching. And the fuzzy switching is what you see here. These are the different fuzzy switching approaches that help you to take composite of these models and deploy the most current model for advanced control of this distillation column. Okay. We could look at aspects. Let me just pause here. Are there any questions, please? Let me just pause. We've been going a little too fast in the interest of time, but
Sir, I will
let me
unmute
pause.
them. If they want to ask the
Sorry?
question, I will unmute them. 1 minute.
Yeah. Please admit them. Let me
put the
get them.
I have put the message in the box. If anyone question, they can ask in chat box also.
Yeah. But if you want to ask, maybe you can just raise your hands and
Unmute them all.
yeah. Any questions, please, up to this point? No? What does this mean? Is this going like bouncers to everybody, or I would like to have at least one question to get a sense of whether what I'm delivering is making sense, or do we need AI to even determine that?
If you are, you can put the question
questions?
in chat box also. Somebody want?
Yeah. Yeah. Are there any questions I can see? No. Right now, chat isn't available, it says.
Chat is available.
It says chat isn't available.
Okay, I will check it.
Yeah.
Chat window is
Oh, Q&A. If I click on Q&A, there are no posts yet. Okay. Okay. There are no questions.
I have unmute to all, sir. If they want, they can unmute and ask the question.
Okay. All right.
Okay, thank you.
Let me just go ahead then. There are no questions. But I would certainly like to have some questions because it gives me a sense of what I'm pitching to all of you. Is indeed something that you would like to hear. Okay. Let's go to this aspect of model plant mismatch detection in advanced process control. Now, typically in advanced process control, you have a controller, and this controller is very heavily dependent on the accuracy of the model. So in an online application, if the controller is not performing well, it could be because there is a huge disturbance, or it could be that consistently the controller is not performing well. Then it could be that the model that is embedded in the controller is not accurate enough. So you need to re-establish or update the model. Okay. So there are tools that are out there which basically monitor the control health and try to ascribe it to whether it's a problem of the model or whether it's the problem of the disturbance, because of a disturbance. Now what we have tried to do is, and that's not an easy classification problem. What I tried to do is use some advanced ML algorithms. Now here is an application. For example, if I have 3 manipulated variables and 7 controlled variables. This is actually an example that we have taken from the kerosene hydrotreater unit at Suncor in Canada. So it has 3 manipulated variables, 7 controlled variables, and 3 disturbance variables. Now, if you look at it in the controller, there is a multivariable matrix that consists of these as output variables and this as input variables. It's possible that in each of these relationships, there might be a mismatch between the manipulated variables and the controlled variables. So how do we look at monitoring the accuracy of these models and how do we detect that a model has failed? For example, there could be a mismatch in this model or this model or this model. There are question marks there. So it was seen that there was several severe performance degradation. This study was carried out way back around in the 2010 kind of a time frame. This is a nice publication that I would refer all of you to. So what we want to do is we want to basically detect channels in which there is significant mismatch. So there were observed by the plant people that there was very poor quality models associated with control variable 2 and control variable 4. There was also a lot of violations that were seen in terms of the control variable limits for a significant amount of time. So then we used some of the regular statistics-based approaches called correlation, Pearson's correlation coefficient. When we did that and tried to correlate the errors in the model predictions with the manipulated variables, it threw up a lot of channels in which there was a mismatch. As you can see, a lot of channels were showing a significant mismatch in the red boxes. Okay. We analyzed this problem a little bit and we found that some of these highlights or flaggings were spurious. Regular correlations has a flaw that if the correlation that you are trying to establish between a causal variables and the effect variables, if the causal variables themselves are correlated, then regular correlation analysis can throw up spurious correlations. So we decided to use a partial correlations approach where it takes care of the correlation that's present in the causal variables. When we did that, it was found that these two channels, that is the channels between control variable 4, manipulated variable 2, and control variable 2 and manipulated variable 3, there was a significant mismatch in these, and which when corrected help in getting a better performance from the model predictive controller. I'll just now, in the interest of time, switch over to another aspect of AI and ML, which is what the current research is. So I'll just skip this. Yeah. Before I do that, let me just take a couple of, case studies before I go to the current advances. Let's look at the oil and gas value chain. I remember I told you that value has to be tracked along the value chain, right? So let's look at the value chain in oil. If you look at the value chain in oil, you basically have production, processing. Sorry, oil is the lower one. Production, transportation, refining, and marketing. Gas is the upper one, production, processing, transportation, and marketing. There are two value chains. You want to basically make sure that as the value chain progresses, the value is not lost due to some extraneous factors. So this oil and gas value chain involves basically, if you look at the upstream, okay, exploration and production, it basically involves a very, very complicated process. Actually, the process is very simple. If I have to describe it, it is like how we drink Coke from a can. You basically produce a negative pressure and let the Coke flow. Here also, you basically produce a negative pressure to let the oil and gas flow. It's very simple as that. But the factors associated with that are fairly complex in terms of both time scale as well as behavioral relationships, time and space scale. We are talking of large reservoirs which contain oil and gas, which have to be evacuated for oil and gas. We are talking of reservoir pressures that change with respect to time. The reservoir pressures fall. And so you need to also look at a hydrocarbon recovery plan, which has a time scale of years. You have a reservoir surveillance, which has a time scale of months. You have optimizing production, which has a time scale of weeks to months. And then you have local control points, which are probably every few seconds or minutes. So there is a varying time scale of decision making where you need to build AI and ML models. If you look at the reservoir itself, the reservoir, as I said, is like the Coke can, which you want to develop for pressure from external factors so that the oil flows. So you need to do a 3D and 4D seismic kind of data. So a lot of data is there, three-dimensional in the space and the additional dimension coming with respect to how this changes with respect to time. So a lot of seismic data, you have a lot of production data in the archive, you have a lot of modeling data. And at the simplest, at the operational level, what you want to do is find the best well target by integrating information from all of this. A very, very large dimension, complex, computationally intensive problem. If you have to solve it, AI and ML approaches can help in building abstractions to these so that you're able to make decisions both on a real time, but also in terms of, these 4 time scales. It can help you to build those abstracted models. Likewise, on the natural gas value chain, I won't delve into that a lot, but you see that there are conventional reservoirs, unconventional reservoirs in terms of the source of gas, and goes through different value chains, and you want to make sure that you track the value across the chain. So there is this entire framework of operational excellence that makes sure that you develop and deploy improved coordinated practices with certain set of improvement indices. If I look at the upstream, I can think about, so let me just talk about the upstream. We're talking of oil and gas platforms. For example, you go to ONGC Bombay High, there are several platforms which we call as assets, each of them producing oil and gas at different pressures, quality, and flow. Downstream, you have the customers. I'll just highlight one of them, C7, which is, let's say, an LNG plant. And, we could have fertilizers, you could have methanol plant, you could have a whole bunch of them that use natural gas customers. Each of them will require gas at different qualities. For example, the LNG plant can accept quality only that is less than 0.75% carbon dioxide, whereas maybe a thermal plant, a gas-fired turbine can work with even higher levels of CO2 that comes in the gas. So each of these assets, they need to be coordinated. Their functioning needs to be coordinated. So I talk about coordinated functioning and delivery of oil and gas across the boundary, right? So I'll just complete this animation. What we need is a coordinated functioning of all of these assets. For example, if one of the assets fails, you have the other assets to make up. You want to make sure that you blend the quality of oil and gas from each of these. That blending is basically another coordinated decision. And to be able to facilitate all of this, you want to modernize the workflow. People are enablers, but AI and ML can also help in modernizing the workflow so that in real time, you basically deliver the right amount of gas at the right quality, right demand, right flow and pressure to the different customers that are present out there. Okay? And so this it requires you to coordinate between operational optimization and workflow optimization. AI and ML can certainly help in all of these to basically get operational excellence. I won't delve into too much of these. I'll just quickly tell you what is done or what we did for a couple of industries. We decide on the performance metrics, establish benchmarks, both theoretical and practical, and then you continuously update the benchmarks to drive operational excellence. Quick case study is, as I said, upstream and downstream. In the downstream, I have taken only the LNG plant, the business segment. There is an enterprise boundary here. For example, transport and delivery is one of the downstream aspects of the LNG plant. The transportation of LNG happens through barges that take the LNG, liquefied LNG, and goes to regasification terminals. If there is a disruption in the schedule of the tankers coming in to pick up the LNG, it has to propagate backwards and the E&P segments have to produce less. So that kind of a coordination across business boundaries has to be achieved. Within a business boundary as well. For example, each of the assets need to coordinate to deliver the right amount of gas. You want to make sure that this is done safely, there are no bottlenecks and instabilities in the chain, and you need to
Probably having network problem. Huh? So wait, he will
Have you
join.
come back?
Yeah. Yeah, sir.
Okay. Yeah. So we are talking about upstream and downstream coordination within upstream, coordination within downstream. Coordination within upstream is coordination between different assets, facilities, and pipelines. Downstream, we are talking about the business segments. This kind of an integration has to be done at different time scales, and there are significant places where AI and ML can play a very strong role. I'm showing you one example from upstream, which we did for oil and gas industry. Unfortunately, I cannot reveal the details, but this is asset 1, asset 2, asset 4, and potentially a future asset 3 coming from here, and an LNG plant that delivers to various customers. The blending between the high CO2 gas header and the low CO2 gas header is something that can be done by coordinating the sources of this high CO2 header, which are the assets A1, A2, A4, A1, A2, and A3, and the low CO2 header, which is A4. I need to schedule the operations of A1, A2, A3 along with A4 so that I get the right quality of gas here. And that's something that is a classification problem that can be solved using AI. That coordination results in safer production practices, improved reliability in meeting gas nominations, and of course, provision for future asset additions. I'll look at a second example where there is a decision making within an LNG plant. And when you do that, so this LNG plant that I showed you for liquefaction has an upstream, a midstream, and a downstream. The upstream basically looks at stabilizing, the slug catching and stabilizing. The midstream is basically looking at acid gas removal, mercury separation, NGL extraction, liquefaction. So all of this cryogenics happen here. And there is the fuel gas system and the shipping and logistics, which is I would say the downstream, completely downstream. Now, if you have to make integrated decisions, each of these within an enterprise needs to be coordinated. And so we had developed this in terms of optimizers at A, B, and C, that basically the arrows show the coordination between them to make sure. A case in point is, for example, the LNG cargo logistics manages internally the inventory scheduling, cargo logistics, but also interact with optimizer A to make sure that the right amount of gas is produced. Alerts on tank tops are propagated. Uncertainty in LNG takeoff. Basically, one has to make sure that you receive less gas. Interaction with optimizer B for the fuel gas balance system. Likewise, these two interact in various ways as indicated here. And this integration across these three assets resulted in reduced fuel gas consumption, which is how much amount of gas we use for fuel, because the LNG plant also runs from the same natural gas. Reduced flaring of excess gases. When there is a flaring, why does flaring happen? Because production is large, but the takeoff is not good enough, so you have to flare. If you are coordinating that, it reduces flaring of excess gas. Extended life of cryogenics. You want to make sure that there are no tube leaks in the methane cryogenics related aspects, which is a fault detection and diagnosis approach in this liquefaction step, which is also done using AI and ML. So opportunities for AI and ML in this kind of a scaled application. Okay. I will now get into some of the research that I have been doing, which hopefully all of you can get excited for the faculty here. We are talking about looking at how do we bring in physics more strongly. And therefore, what I've done is titled this part of the presentation as an alternate look at incorporating physics into AI and ML approaches. Okay. So mechanistic models, ML models, if you compare them, mechanistic models have certain uncertainties, incompleteness, they're computationally pretty expensive. ML models do rely on the quantity and quality of the data, but they seldom utilize prior knowledge. Can we make the best of both? Okay. So first, what is the big advantage? First is in complicated applications like aerosol dynamics, for example, or nonlinearity in CSTR, or a tubular reactor, or a catalytic, the application of a catalytic rod where there's a reaction happening, or in large scale plants where, it's a DAE and it's typically computationally expensive to solve. If you look at some of these applications, and the ML models typically represented by neural networks, and what we are proposing here is physics-informed neural networks and graph-based neural networks. Okay? But to be able to enable this advancement, let's understand what was the first paradigm. First paradigm was empirical science based purely on experiments. This represented knowledge as data coming from experiments. In the second paradigm, we saw theoretical science where physical laws, mechanics, thermodynamics stepped in to be able to get a better knowledge of the systems. In the third paradigm, we said, okay, let's delve deeper into second and look at computational science, which looks at density functional theory, molecular dynamics, and the like. As we go further, are there opportunities to bring all of this together, AI, statistical learning, data mining, pattern and anomaly detection, but representing the physics? This is where we want to kind of look at in a two-way communication between models and the current paradigms in artificial intelligence to augment the current paradigms so that we are able to get more reliable AI models. So here is a quick overview of hybrid and physics augmented models. In the one way to bring in the physics into the system is, let's look at the first application, which is the aerosol dynamics. In the aerosol dynamics, what we have is a very complex model, which takes quite a bit of effort to solve computationally. Can we empiricize some of the time-consuming steps? When we delved into the aerosol reactor model, the aerosol coagulation model was the one that was a rate determining step computationally. So could we empiricize that using ML? And this hybrid model can then be used to solve that in a faster time. That is one class in which we can bring in both data as well as the artificial intelligence based approaches. The second is we actually augment the when we train an AI model, we augment it using the physics-based models. One example you saw was in the polyethylene reactor. The second is, can we do physics-constrained learning in neural network-based modeling? So in a typical neural network-based modeling architecture, you minimize a loss function that is constructed based on data. can the loss function also bring in the physics-related closures in the mass and energy balances? That's something that we say is an additional constraint. So we call it as physics constraint learning in neural network-based modeling. Potential applications, for example, physics-inspired neural networks, or even in model predictive control, that could be done where we use underlying physics and mechanistic models. So this is physics augmented surrogate modeling. The third is that my physics is reasonably known, and I have also data that is very, very uncertain. Okay, but I know the cause and effective relationships. In a cause and effect relationship, the causal relationships I know relatively accurately. Can I represent that information using a graph? And can I build graph-based neural networks, which can then be used for fault detection and diagnosis, which is knowledge-based graphs to augment neural networks? This is the third class. Of course, there are many others that can be done that combine first principles knowledge and data in more creative ways. But here is one suggested approach. Just completed a body of research. My students, Rahul Patel, Parth Brahmbhatt, contributed to some of the study in this, and there are publications that I urge you to look at. Let me go into a little bit of a detail in each of them since I'm talking to faculty here. There is, for example, the aerosol model that is represented by a generalized differential equation. And the solution of this is significantly complex, huge burden associated with the GDE, the generalized differential equation, that results from the coagulation term. So as I said, can we empiricize the coagulation coefficients evolution through using a neural network model and then incorporate that into this differential equation? Because that term is something that is taking a lot of time to solve. Can we simplify that? And in this case, we use, of course, a neural network for the empiricizing of the coagulation term, and then qualify in terms of the input and output a regular neural network model. And if we have to do that in the context of the coagulation model, so here you see, this is a traditional neural network which we try to train. Here what we try and do is we bring in the coagulation model explicitly along with the ANN and come up with coagulation coefficients that are learned from the data using this hybrid ANN network. And when we try to do that, the evolution to the ANN model and the very computationally intensive moment model or the sectional model, there is a relatively good meeting, but at a relatively higher computational efficiency in being able to predict them. It's a lot faster. We applied this for a furnace aerosol reactor that basically looked at, modeled them using three different approaches and found that the ANN model did quite a reliable job at a lot less computational time. If you look at, the computational effort that is required there. So you see that the sectional model takes about 3433 seconds. Moment model is a little less accurate, shorter time. The hybrid ANN model takes a time that is similar to the moment model, but gives you relatively much higher accuracies in being able to solve them. The same CPU time that's shown on a log scale for both of those. Let me look at some of the applications of this. We did state estimation using physics-constrained neural networks. This is the second application where in a traditional data-driven neural network, we train the neural network using purely data. In the physics-informed neural network. Hello, yes, please.
Yeah, your screen is not visible. Are you presenting something? I think,
Says here that I'm presenting.
but I'm not able to see since 10 minutes.
Oh, you should have
But it is
stipulated
moving,
that.
madam. On my end, it is
Sorry?
moving.
No, I
That
am
is
not
here.
able to see any screen.
Can you
Yeah,
see
now
it
it is
now?
coming.
Okay.
It's on the way.
Was that the problem with others as well? I don't know. After
No,
the disruption, maybe.
no, sir. It is visible to me.
Okay, okay. Maybe in some cases it was not. Sorry about that. I should have probably after breakage I should have reshared my screen. Anyway, So
Thank you.
now,
Now I see. I
phys-
can see.
yeah, thank you. Physics informed neural network, what you do is you basically just look at the closure. So the loss function is formulated as a closure of the mass balance equation, and you train the neural network for that. But in a physics inspired neural network, what you do is you train it both on the data and physics. So if you look at the objective function here, this is the loss function associated with the data. Here is a loss function associated, these two loss functions are associated with the physics of the system. So what we do is in a physics inspired neural networks, we try to minimize this revised loss function as opposed to the conventional neural networks that only looks at L1, the first term over here. Okay? And this gives us relatively more accurate uh, uh, AI models that can be used. For example, in state estimation, what we were able to do was show that there is a higher accuracy that's achieved in state estimation using physics constrained neural networks as opposed to just empirical neural networks or the regular filtering approaches. Likewise, there is an opportunity to do optimal control. For example, an optimal temperature trajectory for a tubular reactor. In this case, the tubular reactor was represented by these model equations, which as you see is a partial differential equation in space. If we include time, it's even more difficult. The objective here is in a series reaction, A going to B going to C. I want to maximize the B at end point. Okay, I want to minimize the side reaction. I want to maximize this first reaction. So to be able to do this and model it, while we try to do this using the regular PDs versus using the PINN model, we parameterize the temperature profiles, and then when we compared the performance, what we were able to show was that the temperature, the PINNs, were relatively insensitive to the time that it took. But the FDM model, the finite difference model, basically scaled with a number of grid points. So this kind of tells you that if I train a neural network based on the combined cost function here, then I'm able to do a relatively better job in terms of representing the physics along with the data, and then be able to get more reliable AI models for optimal control. Okay. So this was the other application I wanted to present here. So again, let me just pause here for any questions before I go to the third part of my presentation. Any questions, please? Any questions on the presentation so far? Okay. Let me just go to the third part of our presentation. It's not in the form of slides, but eventually I'll get it in onto the slides for all of you to go through. But the third part of the presentation is to do with how do we incorporate the qualitative information in the form of physics for fault detection and diagnosis. This is, as I said, some of the work done by my PhD student Rahul Patel, which actually can highlight. So I'll just quickly go to. Just give me a minute here. In the meanwhile, I'm open to questions. Please do ask those questions if you have any. Okay. Just give me a minute here. I'm trying to pull that out. Yeah. Yeah. So in graph-based neural networks, what we are trying to do is we are trying to represent the cause and effect relationships using this kind of a graph, several measurements, and this is basically taken from the Tennessee Eastman problem. So in the Tennessee Eastman problem, as I said, there are 52 variables with respect to time, and qualitatively we know which variable, at least through the equations, we are able to represent that. Although the equations are not accurate, they could be in a qualitative manner be able to depict the cause and effect relationships. If we are able to represent this using knowledge-based graphs of this kind, then this can be transformed into appropriate matrices, and we could use graph convolution networks to be able to build the kind of cause and effect relationship that we wanted to model. And to just show you a quick result of these using conventional approaches, I mean, just skipping through his thesis here. Let me just show you some of the important outcomes of this to a table. Uh, yeah. So if you see here, there are a number of architectures that can actually be used, and in each of these cases, what he's trying to do is look at the F1 score for each of them, and what one could do is for different types of faults, the different 20 kinds of faults, while a number of other approaches can be used. In this case, the graph convolution network was able to give consistent F1 scores in almost for all of the fault scenarios using cause and effect relationships. Otherwise, they would have required a huge amount of data to be able to train the other kind of neural networks. So, one could also use, when partial knowledge is available, one could use graph convolution networks in the form of representing cause and effect relationships, and use that to be able to detect fault detection, to detect faults in a relatively easy manner. So that's the third part of incorporating physics. We saw the first part, as I indicated here. The first part was basically to look at, just pull that out. Sorry, yeah. The first part was basically to look at, I'll share my slide again. Yeah. As I said here, the first was in a fairly complicated ML first principles model, whether we can bring in machine learning to empiricize some of those relationships, constitutive relationships, and build a hybrid model. The second is to build a neural network either purely on first principles model, we call that as neural ODE or neural networks based models. The second is to augment that with data. So both of those forms, depending on the kind of constraints you do in the neural network training, you could have both just physics and closure of the physics in the loss function, closure of the physics and closure of the data, minimizing the data predictions in the loss function. You could have either of those, and those could be used to build physics augmented surrogate modeling. The third is when we just have causal information about the cause and effect relationships, we can use graph-based neural networks to do, for example, fault detection and diagnosis, but also various other applications. Then we can be creative in combining data and models in several different ways. I just show you here 3 of them, but there could be several other ways in which you could represent them. For example, I could combine graph-based with, for example, in fault-tolerant control. I could simplify the task of determining or quickly identifying the faults using graph-based, and then to really get into fault-tolerant control, when one could use, the physics augmented surrogate modeling. And so various creative ways, depending on the rigor of the application, the needs of the application, one could combine first principles physics with data to be able to build this kind of models. So that is my perhaps the last slide on this. I just want to pause again for any questions, but if there are no questions, then let me present to you the last slide, which is really the challenge for all of us AI and ML practitioners, researchers, especially when we bring IoT and IIoT and the like. And this is the challenge problem, that can we deliver comfort control? In a very traditional sense, comfort control is, for example, I'm sitting in this room The comfort control is based on a combination of the airflow, the temperature, and the relative humidity. And I can do comfort control by appropriately adjusting the temperature, the humidity, and the airflow to get any level of comfort I want. But if I want to have AI and ML do this, I can do it for the comfort problem in this room. But if where humans are in the loop, and especially with going into IIoT and IoT, sorry, the industry version 5.0 and 6.0 that talks about cyber physical systems, massive parallelization, and where the human hand meets the robo arm, if you are trying to bring in that kind of a sophistication in industry 5.0, 6.0 and the like, the challenge problem to all of us is that can these systems mimic and deliver the comfort of a mother's touch? That's something that I leave it as a challenge to all of us. But I'll stop my presentation here, but I'm happy to take any questions. Thank you.
Participant, you can ask the question either orally or in the chat box also. I will convey.
Yeah. Okay, I can see some postings here.
Sir, I had a doubt
No,
regarding the last point that you were discussing about comfort control.
yeah.
So, is it just your personal idea about it, or are there any researches going on industrial level regarding it?
For that particular application of a mother's touch, I don't know of any. But in the comfort control problem related to HVACs, yes, there is a lot of work. For example, the comfort as a criteria or a metric cannot be measured, right? I mean, I can say that I'm very comfortable in this room, but if somebody has to ask me a quantitative measure of that comfort, there is none, right? So there are methods that look at ways to represent the comfort through a combination of these three parameters that I mentioned, which is humidity, temperature, and velocity of the air. For example, if I'm for a poor man, the comfort is really sitting below a fan at top speed because he or she cannot afford a AC, let's say. But AC, the fan is at the least of the energies. The velocity can provide velocity of the air can provide comfort to a certain level. But beyond that, beyond the speed of the fan, you can't change the comfort in any particular way. If you now bring in, let's say, air conditioner, an air conditioner requires power. It's dependent on, I mean, the next cheaper cost option, I would say, would be a desert cooler, but it doesn't work in all environments, especially humid environments. So then you want to go for an air conditioner, which of course also involves higher power requirements, but then you are able to more crisply, achieve the comfort control by a balance between the humidity of air and the temperature of air, which combined with the velocity with which it throws out the air can provide a comfort control. So if you see some of these ACs, they have both fan as well as temperature. They don't as yet have humidity control. When you bring in humidity control, you can see that you can achieve a lot more comfort at relatively higher levels of humidity than what's achieved in the air conditioner, which requires lower power and is relatively more cost effective. So I would say that in this loosely defined sense of comfort, there is a play between these two parameters with the overall view of minimizing energy. Some of the research in building automation systems are focusing on this area of comfort control. I hope I have answered your question, Mayuri.
Yes, sir, it was satisfactory. Thank you for.
Thank you.
Sir, I have one question.
Yeah.
Sir, in distillation column for enriching the product, we generally play with the reflex ratio. Considering
Right.
the AI view, what data we can consider for the enriching the products? So the one slide
Okay.
you have mentioned the distillation column.
Okay, so I kind of breezed through that. My apologies. But if you're talking of, let me give you an analogy of, let's say, 100-meter dash, and our icon for that is our Payoli Express, PT Usha. If you're looking at a 100-meter dash and you're trying to improve your speed, let's say to begin with, you're at 20 seconds and you want to bring it down to 15 seconds. With a reasonable amount of practice, you can bring your timing down to 15. If you want to bring it down from 15 to, let's say, 12, you need enormous amount of effort. From 12 to 11, 11 to 10, and 10 to 9, and so on, the kind of effort practice required is much, much larger. A high purity distillation column is like that. At relatively lower levels of purity, for example, in distillate, if you want a distillate composition of 0.95, 0.96, relatively easy in terms of the reflux. As the purity increases, I need to reflux more and more. That means higher condenser load, higher energy requirements. In a high purity distillation column, I'm working at two or three nines, or sometimes even 4 nines, 0.9999, right? That requires an enormous amount of energy. What does that mean in terms of control? It means that I have very, very long, when the energy requirements are large, the reflux flows are large, the entire distillation column dynamics change. The reboiler heat duty goes up. The traffic in the vapor and liquid changes quite substantially. The dynamic models are no longer effective. At really high purity zone regions, I need models that are representative of the flow conditions at that time versus at relatively lower purity conditions of 0.95, different models are needed. So what we do is we basically look at representing the dynamics in each of these regions as in my application, at 4 different models. But the important point to realize here is that in an actual operation, the region can swing, right? It doesn't have to belong to one model at all, depending on the disturbances and the like. So if I really want to have a very accurate control of the distillate quality, I need to make sure that I use a composite of these models, a combination of, let's say, the third or the fourth model in the high purity region, or sometimes in the second, third, and fourth, depending on if I'm doing a transition between 2 grades in a distillation column. If I'm going from 0.95 to 0.99, it's a transition. I need to transit between the model representative at 0.95 to a transition that's more representative of 0.97, 0.99, and then 0.995, let's say. So 4 different models. But to make that transition, you need to gradually switch between these models. And that is where, fuzzy logic, fuzzy reasoning, and fuzzy transition, because fuzzy reasoning, what it helps you to do is reduce the belonging to one model and increase the belonging to the other in a gradual manner. And so that kind of a fuzzy reasoning approach can be used to schedule the controllers in such a way that at the high purity region, you get a very, very accurate and reliable control. And AI can help build this, whether it is 3 models, 4 models, 5 models, how many models you need. AI will help you determine that. It will also help you to determine what are the models that are actually valid in the regions. And it will also help you to manage the transitions.
Okay, thank you, sir.
Good afternoon, sir. Can you recommend some research areas where undergrad students can gain hands-on experience with the AI ML techniques, or something which is level of the undergrad students?
I would say, in fact, we are trying to propose this even in the curriculum, that, for example, just take the thermodynamics course. It's once you understand the state equation, the equations of state and the thermodynamic property prediction models, it is basically a problem of capturing the empirical relationships, especially for non-idealities, the vapor and gas phase, the fugacity related aspects, activity related aspects, especially at low temperatures and high mixture densities in the gas, and the like. The conventional property prediction models don't work as well. Can we enhance the property prediction using, the understanding of both the current literature as well as new data that can be generated through VBLE studies? And can we build a very, very reliable property prediction model? And that's a very simple thing to incorporate, let's say, in an undergraduate thermodynamics course. But as you get into process control, for example, or you get into optimization, for example, the student at the undergraduate or even at the MTech level will very soon realize that computational time becomes a very severe constraint. For example, if I'm solving a very stiff nonlinear differential equation, so the complexity comes because there is nonlinearity. The complexity comes because there is stiffness. What is stiffness? Some of the time constants in the variables are not the same. Some of them are very fast, some of them are very slow. So if I have this kind of an equation and if I want to solve it and pose the student a problem of optimizing that system, there are ways by which you can actually segregate based on time scales, segregate based on non-linearities, and then use the optimization algorithm to solve them. So this can be an excellent undergraduate, senior undergraduate or a MTech thesis problem that they can focus on in these aspects. So I would say that every course, be it in thermodynamics, be it in fluid flow, be it in reaction engineering, all of these could have a small module where AI models can be brought in, especially in the empirical aspects, and they could be taught to combine these AI models with traditional differential equation models or partial differential equation models and understand the benefits of what AI brings in.
Thank you, sir.
Participant, any question? Okay, sir. If there is no question, hello.
Yeah. Yeah. Is there a question? Sorry, I couldn't.
I am asking. I think no question, sir. Okay. So on the behalf of the Chemical Engineering Department, I extend our heartfelt gratitude to Professor Gudi, delivering an enlightening and thought-provoking sessions. Your expert insight and systematic approach of explanation how artificial intelligence is shaping in modern chemical engineering practices were highly informative and academically enriching. The session greatly benefited students and the faculty, like bridging the theoretical concept with the real world industrial application, which he sir has explained very good way. He has given the data reconciliations in the process industry, data clustering of the problems, and qualitative informations. So we sincerely appreciate your valuable times and efforts in shaping your knowledge and experience with us. The session was truly inspiring and intellectually stimulating. Thank you once again for your distinguished contribution. Thank you, sir.
Yeah, thank you. I think there were many questions, but one of the things I would like to suggest is that, while this course exposed you to a lot of possible ideas, these are only possible ideas. Your creativity can help develop this even further. So please do feel free to get in touch with me in case you have any questions, any aspects that you want to explore. Certainly, we can work on furthering, because AI, as I said, needs to be improved further. AI as an artificial intelligence needs to be improved further in terms of augmenting first principles knowledge. We can call it augmented intelligence. That's something that we all should collectively do, because traditional data can do only as much. There is a lot that can be achieved by bringing in the physics, which as domain knowledge that we have certainly needs to be represented. So that's something I would ask you to delve into, and happy to answer any questions further even beyond this session, and just be in touch in case you wish to have more clarifications.
Thank you, sir. Thanks for your supports.
Thank you.
So participant will provide the feedback link after this. I will post in the groups. So you fill and send to us.
The next session, sir, can you please announce for the next session?
Okay. So next session will be start sharp at 2:30.
Participants are requested to join with the same link for the next session.
Okay. Thank you, participant, for participating. We will provide the same link at the 2:30. We'll meet at 2:30 after the lunch. So I will end the meeting, madam.
Yes, sir.
Okay, thank you. Thank you.